Hi, welcome to Cloud Native Live, where we dive into the code behind Cloud Native. I'm your host today. My name is Whitney Lee, and I'm a CNCF ambassador, and I'm a developer advocate at VMware. So every week, we bring new presenters to showcase how to work with cloud native technologies. We'll build things, we'll break things, and we'll answer your questions. I'm so excited this week. We have Justin Barksdale and Oz Tiram here with us to talk about how to use two-node HA for Edge Kubernetes, a new approach. So I'm super psyched. Now, as always, this is an official live stream of the CNCF, and as such, it's subject to the CNCF Code of Conduct. So please don't add anything to the chat that would be in violation of that code of conduct. It's really easy to keep track of. Basically, just be kind. Be kind to each other, be kind to the presenters, be kind to me, and I'll be kind to you too. So, friends who are joining us live, please say hello in the chat and tell us where you're from. It's so cool that we have a global community here with us each time. And as always, if you have questions during the presentation, please do post them in the chat. We're going to have today's feel like more like a conversation, and we're going to go ahead and answer your questions as they come in today. So with that, I'm going to hand it over to our friends Justin Barksdale and Oz Tiram to kick off today's presentation. Tell us about yourselves.
Hi, everyone. My name is Oz Tiram. I'm a principal software engineer with the advanced project team with Spectre Cloud. What we do in this team is usually explore different cloud-native technologies and see how we can bring them to our customers. And hand it over to you, Justin.
Hi, thanks, Oz. Yeah, my name is Justin Barksdale. I am a principal architect on the sales side, so I help support our customers and help them design and implement solutions around our products. So I'm happy to be here. I do want to kind of go through a quick agenda. So, we are here to talk about two-node HA at the edge. Our focus is around edge in this particular conversation. I want to talk a little bit about what the three-node problem is. So why three nodes really doesn't work for some customers or many customers that we talk to. What are some alternatives that we've come across as we were sort of building this solution or going through the solution? What solutions have we come up with? We have a couple of different options and a couple of different demos to go through. And then what are next steps? So with going into that, really what's the problem with three nodes at the edge? We've been running three nodes or more Kubernetes for quite some time. What are the challenges that we see at the edge and why is this really kind of important? And I think the first thing is really to talk about the scale. Edge scale is much, much more massive than what we see in data centers or in just clouds. And a lot of this drives around cost. The number of nodes I have at the edge drives up cost for me to do certain things at that particular location. And oftentimes three nodes becomes overkill for what we need in terms of what the workloads require. So we're buying an extra node just to support the ability to have high availability. The reality is the workloads themselves don't take that much. There are that many resources. Could we do better? When you think about edge and thousands of clusters, tens of thousands of clusters in some places, every time you add a third node, that just adds up. And the need to have that third node for HA only really kind of takes away from the model that we've taken in terms of build your infrastructure to support your application versus having to have this high availability extra node. And that thousands of nodes adds into dollars. When you think about the types of devices being deployed at the edge, whether they're small form factor devices, single socks, they're still hundreds of dollars each. And we've seen most of them between $500 and $1,000. So when you think about that and you have 10,000 locations, it just adds up and becomes very, very expensive to achieve HA. And most edge deployments that we're seeing in terms of how we're replacing are just two node, virtual machine hosts running some hypervisor. And so a lot of customers want that same kind of pattern. So really, what's the problem? And if you think about Kubernetes and how the database is interacted with, it is a key value store that requires a quorum typically. We see, so the odd number control planes. Quorum is just the minimum number of nodes required to form a majority. So in the case of a single node cluster, you have one node is the majority. In the case of a three node cluster, two nodes would be a majority. And so a 3-node cluster can afford a single node failure. But if a second one of those nodes fails, then we run into this problem of the databases in read-only. The applications continue to function, but I can't make changes. And those changes include things like promoting etcd or telling etcd that, hey, this is a leader, or deleting nodes. You can't do any sort of etcd operation when the cluster is in an impaired state. And so when we looked at this from a design perspective, it was kind of, what are the considerations that we want to look at? We focused on K3s first, primarily. Again, we're talking about edge, so we want to keep the footprint as small as possible. Application high availability is the most important thing. So we don't necessarily care if the control plane goes down for a period of time. Of course, it needs to be recoverable. We need to be able to replace nodes. We need to be able to do actions that would warrant kind of having high availability. But if we lost the control plane for a period of time, 5-10 minutes, that was not something that we were really concerned with. All right. So with that, I'm going to turn it over to Oz, who is going to talk through some of the etcd alternatives before we come back and talk about, our solutions as we presented them.
All right. Thank you, Justin. When we start looking at this project, we thought, okay, we know there's kind, which is a component in K3s. So how about we use that to replicate a relational database? So for those of you who don't know what is kind, kind stands for kind is not etcd. It's a acronym. And it's basically like a shim where you can stick between Kubernetes API server and a data store. Originally, kind supported SQLite, PostgreSQL, MySQL. And in recent months, there's also an option to use NATS as a backend. And we thought, let's try, let's give it a shot. Let's look at what we can do if we can use PostgreSQL or MySQL. But the thing is with those network databases that we start looking at that there's like no single understanding or solution to achieve high availability. If you look at this link below here, we put in the presentation, there's like about just in PostgreSQL 16 different ways or even more to achieve high availability, and each of those high availability modes has a choice that compromise you have to understand. So what we want to achieve basically is the following. We want to have like a Kubernetes, a kind, and some kind of like a network database in the end. And ideally, we have high availability of the control plane. So we can insert or update or delete records in kind or the database from both nodes. So this is the ideal state we want to achieve. And so imagine in between those two nodes, there's no etcd, there's some kind of like a database. We don't know yet which. And to choose which one, we had to kind of like go on to this understanding what is all about in PostgreSQL or MySQL when we talk about high availability. So first of all, relational databases can do a logical replication or streaming replication, synchronous application, or asynchronous replication. There's also like a streaming and logical, synchronous and asynchronous. You can also do like connection pooling to improve the availability of your Postgres or MySQL. And you can also have like a proxy and load balancers between the client and the database. So let me just like go into a little bit of detail of what does these types of high availability mean, okay? So the first thing is you have logical replication. You replicate from a primary database to a secondary database an object. An object can be a column, a table, or a complete database in your database management system. So obviously, first of all, you see that it doesn't really bring us to where we want to be with like two control planes on two nodes at the edge, because with logical replication, we can only write and read to one node, and the secondary is read only. With streaming replication, it's similar, but we don't just replicate an object in the database. Rather, I'm sorry, apologize. A few slideshow. Okay, apologize for that. So with streaming replication, we don't replicate a single object, but we replicate the whole database system by replicating the write-ahead log of the database. So there's a process on one system that kind of like sends the database actions over the network to a subscriber on a secondary system, which then sees what actions the primary database did and writes them into the system here. But again, on the secondary, you can only perform select actions. So it's kind of like just a read-only. The next thing you have to consider with those high availability system is just like asynchronous versus synchronous. So with logical or write-ahead log replication, you can insert in one node, and then there's a secondary which takes those actions after an interval of time and writes them to the database. That means that, again, we don't have two control planes, and there's a delta of time where the data is inconsistent. So there is no, if the database here, the primary caches, there's a chance of secondary losing some data. So with that, to mitigate that, there's a synchronous application, which is a little bit more complex. The client performs an action. The action is propagated to the secondary, which then sends an acknowledgement to the primary, and then only then the client gets like a message of success, that's insert, update, or delete, arrived successfully on both nodes. That's obviously, there's a lot of room here for things going wrong. So it could be like a network between the client and the database. And again, from primary to secondary, there could be loss of data. So there's a complexity here, which you have to consider when you go to synchronous replication. Again, for us, using MySQL or PostgreSQL with this kind of replication, it's a no-go because we didn't have like the availability to have two control planes. Another type of high availability is with relational databases is like having improving the availability of primary database by having some kind of a load balancer or proxy between the client and the database, which distributes requests by the type to the right database. So a proxy could kind of like see, okay, you want to select something. So upon my knowledge of your previous request, I can either send your request to primary or secondary, and you can also have like a tertiary and quaternary, like a third or fourth member with the setup, which improves the availability of the database in general. But that's kind of high availability of database system, which is not relevant for us with more nodes, because we want to have, again, two control planes on two nodes at the edge. To make things worse, many high availability solutions on relational databases require actually a quorum by having a console or etcd at the background, which synchronizes the database at the background. So we kind of like, okay, network database don't work for us. Let's look at those things. Of course, if we choose any of those solutions and we give this to the client, we need to have the right mental model or application model that understands what kind of application or workload is required or acceptable for this type of availability you want to have. So obviously, it's a complex thing to choose between all of those systems. And to make things worse again, there's a complex failure mechanism. So if the master fails, it's not just like with etcd that the primary goes away and then the secondary is automatically promoted to the master. So again, we weren't really sure we want to go with network databases, so we looked at the last option with Kine, which is SQLite, and we thought, okay, we know that we heard of SQLite over the network, but looking closely into those networked SQLite solutions, they all require a quorum and they use etcd or some kind of raft under the hood. For example, Arculite from Canonical uses its own raft implementation, but that just means that if you take micro Kubernetes with Arculite under the hood, you have to have 3 nodes at the edge. Then there's like other solutions of replicating SQLite over the network. One of them is Lightstream, which is active-passive replication of the network, which we almost looked into it, but then by chance we bumped in a nice, interesting project, which is called Mammut, which I want to introduce to you. Mammut is a SQLite replicator over the network using a message broker called Nuts. It's extremely simple to set up. All you have to do is start a process and point it to your database, and it takes care of the rest. At the same time, you can do this on another database, some of the network, and tell it, I want you to subscribe to a publisher of Nuts, and it will take care of everything else. What was really attractive in this project for us in the beginning, that the replication is two-way, so we can have, like we wanted, 2 control planes on 2 nodes. You can check out the introduction of Mammut, and I don't know if many of you are familiar with CDC. CDC stands for change data capture. You can do this with any kind of database by sticking a message broken behind the database with Kafka, for example. But Nuts is embedded, so it's embedded into Mammut, so it's really lightweight and affordable for the edge use case. How does it work? It works in the following way. In theory, you have an SQLite database and you can insert, update, or delete stuff. And when Mammut starts, it creates a collection of triggers on the database. So every action on the database is triggering a message into the Mammut leader. On the other side, we have a Mammut folder, which subscribes to those messages here. And it says, okay, there's an insert here on this side. I will write this insert here. At the same time, the client can also publish those messages to the broker. And if there is an update on this side, on the secondary node, then it will write it to the primary. So this is what we thought in the beginning. Eventually, we realized that Mammut cannot do 2 control planes, and only after playing a lot with Kine, we realized that the problem is not Mammut itself, is a transaction mechanism which is incompatible with this synchronous mechanism on both sides, because if you start a transaction here and it's published here at the same time, a transaction goes here and starts, there's kind of like a deadlock between the 2 nodes. So as a compromise, we started looking at Mammut for replicating SQLite on the nodes, but we go with a single control plane because of this locking problem, which we don't have a good solution yet for. With that, I think I transfer again to you, Justin.
Yes, thanks, Oz. Appreciate that. So I want to kind of go through what our solution looks like as it is today, and then kind of where we're going with it. And again, as Oz mentioned, our goal is to focus on how can we achieve high availability of the control plane and our applications. However, at the current moment, we're looking at the evolution of that in terms of, well, can we just do this with single node control plane and have some type of failover mechanism leveraging Marmot? Now, there are some implications that we have to consider, and one of those being, we're focused again on the application, but the application should be designed in a manner that survives losing one half of it. So, for example, having replicas on one node and that node fails, doesn't really help out if the control plane's down, as the application can't fail over. Certainly, Kubernetes timers need to be tweaked. There's a lot of things to go into this, but fundamentally, the goal is to say, we have an application that can run on any one node at any one time, and there's no dependency on the other node. The control plane high availability, as I mentioned, can be down for some period of time. We look at it like between 5 and 10 minutes is okay. And stateful applications would need very careful design considerations, and we really weren't targeting those types of applications, at least initially. So our architecture looks something like this. I'll talk through and go through a demo in just a moment, but fundamentally, we have two nodes. One of them we label as primary, the other one we label as secondary. The primary node has our agent, which we call stylus, that runs on it and is doing state checks and things like that. And it's fundamentally responsible for determining when it needs to fail over. So in the case of the secondary node in this particular slide, the secondary state checks are taking place when it can't reach the primary node for some period of time, or some of these state checks fail. For example, we ping the alternate host, we look for the default gateway, we try and attach, or can we connect to the API server, those types of things. When a certain sequence of those takes place and the state has failed, then we initiate a failover, which in turn tells K3S to point your database to your local copy, which is what's on node 2, and then resume any kind of replication that would have been happening back to node 1. So we kind of flip the role of how this takes place. So node 2 subscribes to node 1's Marmot instance, and Marmot is responsible for doing this replication. All right, and then kind of going into the next step, what happens during a failover? Node 1 dies. You'll see like node 2 continues to run. Again, the application, as you'll see in the demo, would continue to function, but there's no control plane. At some point during that timeline of state checks, the control plane will switch over. Node 2 will promote itself and become the leader in this particular instance and begin that replication, as I mentioned. When node 1 comes back online, you'll see that it will realize that it's in a state that it shouldn't be in, realize that node 2 is the leader, and that state engine, that agent that we have, initiates a demotion. So it tells it, hey, you're no longer going to be the leader. You need to become the secondary node and go forth, right? So with that, let me kind of go through a quick demo. I want to set up a couple of things here. One is we have our environment, which is called Palette. I have a cluster that is deployed that I've called 2 nodes. So it's just a 2-node cluster. And inside of here, you can see we have 2 different node pools. One is a master pool or control plane pool, and the other one is a worker pool. And this is just running on a couple of virtual machines in our environment. But the concepts are the same. One's labeled primary and one is labeled secondary. What I'm going to do is, because of the time that it takes, and the timers and stuff aren't tweaked 100%, the time that it takes, I'm going to go ahead and kill, as you see, node 2 is labeled as the primary here. I'm going to go ahead and stop node 2 on my VMware environment. So just stopping the node. We'll let the process go through of it failing. So I should be able to attach to my application, which is a very basic app that's just kind of showing the representation of both nodes, and then again, and showing where we're hitting. It has 10 replicas, and so we'll see this in the demo. I have a recorded version of this, so I'm going to let this take place right now, and we'll move to the recorded version that shows more in depth about what we're doing. So, as again, going to our architecture, we have this primary and secondary concept. If I hit play, we'll go through, you'll see a couple of things, and I'll pause and just kind of highlight them. In the bottom right-hand corner, you see the logs from node 2. So in this case, node 2, you can see the state of which one is the control plane in this particular instance, which is node 1. And on the left-hand side, you can see I have 10 replicas of a deployment. And again, these just kind of, they're represented as being across both nodes, but they just kind of bounce back and forth depending upon what's happening. So I institute that shutdown that we just happened, and you'll see, showing the liveness checks and all of those things. But when the shutdown takes place, node 2 initially says, oh, my liveness check fails. And you can see the health check failed. It's failed one time. We'll do this 3 more times. And if we're still below the threshold though of 3 health checks. And so we'll keep checking. These are timers that are tunable by the settings on here. We have them set to do this every 30 seconds. So every 30 seconds, the health check takes place. If it fails once, it's okay. It fails twice. So basically there's like 1.5 minutes or 2 minutes before an actual failover event, which is why I recorded this and just kind of talking through it. But we'll cut ahead and see, okay, the failover, as you notice, the nodes themselves, the control plane is down, which is the expectation. Again, as I mentioned before, high availability of the control plane itself is not something that we're focused on at this moment. We're focused on high availability of our application, which you can see in the top is still running. And we'll see that only node 2 is we're only seeing node 2 pop up. Now, on the bottom, we're noticing that some other error messages are happening, that additional liveness pros come in. The failover took place. So node 2 realized after 4 failures, I need to become the leader. I need to promote myself. And it's promoted itself. And you can see, we're showing those deployments. There's still the timers within Kubernetes haven't timed out and flagged the devices on node 1 as being there. But you'll notice the leader is now, or the control plane is now focused on the node 2. Node 1 isn't ready because node 1 is still shut down, right? There's no concept there. So I'm powering back on node 1 at this point. What we'll see is kind of like a conflict moment where you can see I'm pinging node 1. At some point, node 1, it comes back and now it's been demoted. So what's happening during this process is I was pinging it. It's coming back online, being rebooted. And when it comes up, it notices, oh, I'm not supposed to be a leader. It's demoted itself, but it's not quite ready yet. I'm just going to go back and to look at the logs of node 1. And we kind of see, okay, well, it pops up and is ready. And we still have this, but all of our replicas are still on node 2. We can use the Kubernetes descheduler and timings to reset this. So based on values within there, I can tell it, hey, I want to, reschedule these nodes. I want to reschedule these pods, on and distribute them more evenly, because by nature, Kubernetes during a failover won't reschedule as long as it has capacity available. So basically just rescheduling those so that we are going back to our previously good state of load balanced in terms of the deployments are split across both nodes. So this is our current iteration of where we are. So if I go back to my instance inside my palette, as I mentioned, one of the challenges is like timers within Kubernetes, how fast things fail over. If you don't have the pods, the pod timers, I'm using Metal LB as a high availability, like load balance kind of mechanism. If it doesn't fail over fast enough, this screen refreshes every 10 seconds. So if it's in between a refresh, then we get that I can't display whatever, which is, again, thinking about the application design. How can we make this more available? Timers being tweaked, application availability, those types of things are certainly things that need to be considered. But this whole process will go through, and you'll see inside of here, once my node 1 becomes, it's kind of going to switch over right now, node 1 will become the leader, and I'm back into a good known desired state. All right. So again, this is the evolution. This is what we're driving forward. Now, we started this out by saying that we want to have high availability with 2 control planes. And so if I think about what that might look like, it is kind of a combination of everything that we put together. And our phase of this looks something like this. recently, Postgres had a new release that allows for synchronous replication between two databases or more databases. And so we've come up with this kind of idea that, well, could we take Postgres just natively and tell it to replicate amongst itself and have two high availability control planes. And so Oz is going to show a demo of this in just a moment. But I just wanted to kind of set the stage and say, this is what we're driving towards, using these technologies to be able to enable our customers at the edge to have high availability, but for both the control plane and the application. So I'll turn it back over to Oz to show a quick demo of our HA control plane model, which consists of Postgres and looks very similar to what I have on the screen here. Oz?
Thanks. Okay, thank you, Justin. So what we have here is I set up a Vagrant lab with two virtual machines, which have PostgreSQL 16, which was released a couple of weeks ago. It's very early, kind of like preview technology for us, that has two databases on two nodes. And you can see in the log messages that I created a publication on one node and there's a subscription on the other node. And what you see here is that I have actually really two control planes, kubectl get nodes. So there's here I can talk to the control plane to get nodes. And if I show you the pods, you'll see that I have, sorry, let me do this, only the columns. So I have VMware control plane, and I have nodes, and something's wrong here. I don't have it's PS the KTS7. Oh, it is running here, but there's only one control plane. That's surprising for me. But what I want to show you is that like I can fail this node here, VM1, and the cluster is still available, because what happens under the hood is that both control planes talk to the same database, and there's an active standby I can switch to. So that would be here, the config. Let's do grep data store, and here I have the same. There was an obsolete bad use of grep. Grep data base for this file again. Oh, that's why there's no control plane here. I really apologize for that. Let me check why is it not started here. Sorry. Scripts start KTS. Let's see if that works now without breaking anything. Okay, I have no KTS.
We promised at the top of the episode we'd break things, so I'm glad you're making me true to my word.
Yeah, I apologize. I thought the Vagrant lab was working.
While you're troubleshooting, I have a question. I don't
Yeah,
know much
go
about
ahead.
this space, so I fear that a lot of my questions today will be remedial. But why do you want to have a control plane on every node?
That's a good question, actually. Well, the reason is that because, as Justin showed, the failover mechanism is quite complicated. Like in the case of Mammut, when we fail over the control plane, we need to change also the model of Mammut. We need to kind of like stop Mammut and make it from a leader to a from subscriber to publisher. When the failed node starts again, it cannot start again automatically as a mammut leader, because you get conflicts, right? So you need to say, no, you can't start like this. You have to change your configuration for your starting mammut again and demote yourself. So this whole kerfuffle of like promotion, demotion was quite complicated to implement, to be honest. And we broke our heads a couple of good weeks on that. And if we could completely avoid that, that would be awesome. And we kind of like push this whole logic of code upstream to PostgreSQL. It would be awesome, because PostgreSQL has I don't know, millions of users out there. And if this works, then it's battle tested. It's not just like something we implemented over a couple of weeks. So it seems that K3S is now working.
Great.
Let me see. K3S. There is K3S, so the config file should be here. Rancher, K3S. There you go. So I have both K3S talk to the same member of the cluster. Okay, and I have PostgreSQL running here on VM2 PSAUX cap Postgres. So you believe me all. So there is Postgres here, and it's there, this node. So now let's see that we have also two control planes, get pods. So this is an imaginary workload I have. Let's see if I have, where's the command, just like with the pod names. So still no two control planes, but it doesn't really matter, because I can fail the control plane as this one on 2 should start, but PSA this there on this one, cap K3S. There is a K3S here too, but it's not running as a server. That is weird. No, I want to look at the systemd unit and see if it's running as a server. KTS service. It runs as a server. Let me do.
I have another question while you're troubleshooting.
Yeah.
Do you have to use K3S, or can you use another Kubernetes distribution?
Well, because we use Kine, we actually have like a prototype that also works with kubeadm. So kubeadm usually expects a external etcd. So we could just start Kine and point kubeadm to Kine. So that should work, and it actually works in our implementation.
Cool.
Okay, yeah. So
Yeah, just to add to that, Whitney, one of the goals is to be agnostic. We started out with K3s because that's kind of, again, where we see most edge deployments, but there are certainly use cases where K3s doesn't fit, for example, like FIPS compliant areas, things like that. So our goal is to try and leverage where we can, having to not do this logic, as Oz mentioned, but also providing some non-dependencies on things like Kine as an example, or K3s, or other distributions, just being able to say, hey, I want to plug today, I want to use this one because I have this requirement or whatever, and not having to worry, does that work?
Okay, I think the problem is actually myself. I just can't see the message of curl here, but I think I'm actually talking to the control plane locally. Let me just check if I'm right here. Justin, can you give me a hint if I can see the actual curl call with grep? Just like I know there's a way to get the actual grep command, the curl command with Kubernetes KTL. Um, mm, let's see if no, it's somewhere there. It's gripping it, but I don't see it. Okay, so let me just. I hope I don't embarrass myself, but I think if I stop M1 here, yeah, the control pen should still work. So what I did to simulate the, I'm not in there, what, VM1, sorry, okay. Um, do you want to ask us another question while it takes the time?
So this is all brand new to me. So I'm just going to restate the problem. So basically, to use Kubernetes on the edge, so all of the solutions presently, you have to run a 3-node cluster, and that just it's often overkill for a lot of different workloads. Which actually leads me to a question right there, which is I remember you saying like stateful workloads are probably not best for this, at least not yet. But what kind of workloads are ideal for a 2-node HA solution?
That's a good question. So I think to just clarify, yes, you can run single node Kubernetes at the edge, but you don't have high availability. So if you lose hardware failure or something like that, that's out of service. And there's some use cases where customers are comfortable with that. They have, I don't need, it's not mission critical. It's just providing some type of whatever. The use cases that we're targeting focus on, I need high availability for my applications. They're designed to run across multiple nodes. And I have built into there the capabilities for those either through their own internal replication, the application's handling, if they're using databases, data replication. But I don't have a need for transactional, like I need things to state between them. We're not sharing state.
Mm-hmm.
My application's handling it. What we're seeing a lot of is think in terms of I have IoT aggregation points. I've got a lot of thinking like fast food as an example. I have a lot of fryers and fridges and things that have sensors and information. I don't want all of those talking to the internet. I just want to use my local device to kind of aggregate, maybe do some pre-processing and then punt it to a cloud to be processed more. Those things turn into additional kinds of use cases of, well, now maybe I want to do some intelligence locally. I need to have that there because if the internet's down, my thing needs to continue to provide information, but I don't necessarily need to have like super high availability all the time, but I also want to have some survivability. So I don't want to do one node,
Okay.
and I don't want to do 3 nodes because it costs a lot.
Mm-hmm.
Happy medium is I want to do 2 nodes and I still want to make changes and I still want to have some of those same functions that I get when I have a 3-node high availability cluster.
So it's important to me that I keep all this information I'm gathering,
Yep.
but it's not important to me that I have it all every second.
Correct.
And
Yep.
so therefore that's when a 2-node solution is good.
Yeah. So while Justin was explaining, I figured out what's going on. So let me show you. So I stopped the control plane and the database on node 1, simulating that it stopped. Okay. Now if I try to get pods here, I do like get pods. I get a timeout, right? So it's trying to connect to PostgreSQL and Kubernetes, the database Kubernetes on this node, which is stopped. So kubectl is failing. And this is the RPCO coming from Kind. But if I look at KTS, it's still running. So I should be able in theory to talk to it. And what I did in the meanwhile is I updated the configuration of KTS to actually talk to the database running locally. So if I'm correct, restarting K3S should reconfigure to talk to the database locally. Now, remember, what I said is that we don't want to have this complex mechanism of like failing over. So if we had from the beginning the local KTS talking to the local database, I wouldn't have to do these actions that I did now. And there's actually an interesting story why we can't do that. I mentioned it briefly, and let's see if it's working. it seems that it's not, or it's taking a while to start. But the idea is that um, you can't do active replication for all kind of SQL queries, and that's if I may share my desktop, my browser with you. When you look at the
We can't see your
log,
browser right now, but when you share, is this, let me,
yeah, I
is this
will
it?
share
Okay.
my entire
Okay.
screen. So
Okay, great. I got
yeah,
Justin's
okay.
screen. There we go.
So the documentation for active Postgres comes with a warning. It says don't get too carried away, and they explain here that you can't do transactions. There's actually no good way to solve this public publish and subscribing with transaction. And we discovered that under the hood, Kine emulates etcd by doing transactions actually. So if we start two Kine, or like two control planes on active replication with PostgreSQL, um, it seems like it's working for a couple of seconds, but after a couple of seconds, there's like a compaction mechanism um, of all the records in the database, and that's done with transactions. So the database goes into a lock, and we really hope that we find a way how to kind of like go around that and see. And I think right now what happens is that I kind of like locked my database. This is why kind doesn't start. So yeah, I break thing, but at least I can explain why it's breaking. Um, I don't. We don't know yet how we are contemplating how to kind of like whether we want to discuss this with kind developers to do this compaction deletion without begin transaction and committing. We are still not sure how to, but eventually we will get this right, and we will have. I'm quite sure, very optimistic that we will have the two control planes running on. Um, two control planes running on two nodes. Yeah. So um,
I have another question that might be silly at this point in
yeah.
the conversation, but why not use an external database if for this level of needing information?
Yeah. So if you think about, I mean, our goal is to keep costs down.
Mm-hmm.
And so having to have infrastructure that runs an external database at a fast food restaurant or a retail location doesn't really solve for that. Now, there's certainly maybe logic where you could centralize and put it in a cloud or something, but then that doesn't solve the survivability element of if my internet goes down, then I've lost my cluster and I can't do what I wanted to do anyways. So we initially toyed with the idea of could we like throw out a Raspberry Pi and have it as running some type of database. But again, now how do you achieve high availability there? Well, now I've got to have some number of Raspberry Pis to be, so it just really didn't solve the problem that we were trying to solve. And then there's a lot of other inherent complexity, as Oz mentioned earlier, with just network databases, latency and availability and those types of things that it just wasn't going to fit what we were trying for.
Okay. And we also, Ferdinand has an answer too, which is latency should be considered for an external database too. So we do have a question in the chat. What if you have an active passive mode cluster? I guess I don't quite understand that, but maybe because I don't know a lot in the space. Can you?
Let's see.
Can I answer that?
Yeah, go ahead, Ross.
Yes.
So it's the same what I said in the beginning when I showed the models of like high availability. You can have primary and secondary, like active passive, with some whatever replication mechanism you do. But then again, as I showed you, you can't have two control planes because the secondary is the passive. You're not allowed to write into it. So you will have to, in case of the primary failing, you'll have to switch over, like promote not just the database. You have to kind of like start a control plane on the secondary, right? So while we can do that, we don't want to do it. We want to have a solution which is simple, and there's a lot of like active passive replication mechanism. We put in the beginning of this presentation a link to the PostgreSQL wiki with many options to how to do that. And it's the same for MySQL. There's no really golden standard of how to doing active passive replication with PostgreSQL. So yeah.
Excellent. Thank you. So I have a question. So I own a successful line of fast food chains and I'm sold. I want all my French fry data to be on 2-node HA clusters. So what should I do to start implementing this instead of using the 3-node system that I am using for HA, for edge HA workloads?
Well, I mean, I would say come talk to us. We have, we're going to be present at KubeCon, of course. So we'll have a booth there that you can schedule, one-on-one demos. We have a room as well for meetings. So if you are looking for, learning more or seeing more or hearing more, as this is an evolving space, feel free to come out there. We also we published we'll have a series of blogs coming out, but one of them published around just 2-node in general and focusing on really what is the challenge and what are we solving for. So a lot of the things we talked about today, but certainly as a next step, I would encourage you to come see us at KubeCon next week.
Is this something that's ready to be implemented now, or does it still need some work?
Yeah, so we're targeting what we're calling tech preview within our platform by the end of this year. So it should be available December-ish, mid-December timeframe, with GAs happening sometime like Q1 of calendar year 24. So our edge-wise 3 nodes, that's all available now, but the 2-node sort of, again, focused on a very specific use case. The 2-node solution, we're still, as you see, actively looking and experimenting and trying different ways to do it.
I love that you're learning out loud with us and showing us your journey. I think it's so fascinating. I think you had a last slide to show off. Is that true? Should I put it up?
Yep, I have it. Ready to go. Yeah, so
excellent. Oh, hey, this is familiar information.
As I mentioned, next steps, reach out to us at KubeCon, schedule a demo. You have the QR codes here, and I think the links will also be posted in the show notes. And with that, if there's any other additional questions anybody has, take a moment. Doesn't seem like it.
So far, we don't have any. Will you restate for me? So I understand why a 2-node cluster and what problem it's solving, but I think what you said was the difficulty of getting a 3-node cluster down to a 2-node cluster is that all of the key value data stores that back up the cluster require 3 nodes, all the ones that exist currently. And so what is the challenge of getting that key values data store down to 2 nodes?
Well, most of them center around RAF consensus algorithm, which requires a quorum. And the quorum, as I mentioned before, is a majority of the nodes to be present. So in this case, 3 nodes needs 2 nodes to be available. But in a 2-node cluster, if you just deployed it with 2 nodes and you never lost a node, it'd work fine. A quorum is there, majority is fine. But if you lose one of those nodes and you need to replace it, that's what it becomes. Because now I can't make any changes, so I have to rebuild the cluster anyways. And so how do we get that down to 2 nodes is we don't use Raft. I think that's kind of the gist. Just don't use Raft.
So, and then we have a question. And so I have another one, but how would this compare to a worker node in the edge and control plane in the data center?
So I think some of the same challenges that we talked about before in terms of if my control plane's in the data center, and one of our goals is that I must survive an outage. If I lose the internet, I need to make sure that my node continues to run. We have situations, you talked about fast food joints. Imagine a fast food restaurant that is in an area of the world that is frequented by natural disasters, and their internet or their infrastructure is impacted, but they happen to be the only restaurant available because they have power, but they don't have internet. But in the situation where my control plane is in the cloud, and I lost power for a period of time, when that node comes back up, it's not going to be able to really do anything. So those are types of survivable concerns that we have, and making sure that the entire cluster is available at any one time with no dependencies on the outside world.
That's great. And to further recap, now we have the two nodes, and the challenges at CD is or those related things are all based on the raft algorithm, which requires at least 3 nodes. So now we need a new solution, and you looked at lots of different ways to replicate data between 2 nodes. And so what you came up with as the best choice was Marmont. And will you recap for me why that was the best choice?
I want to caveat and say I don't know if it's the best.
Okay.
It was
Okay.
the first choice that we found. That
Yeah, it was the first thing that worked. So no, really. So we could have gone with Lightstream because it's very, very simple, and it's a bit older than Mammut and has a big I think usage. But when I bumped into Mammut, it had a very attractive tagline, and there's the fact that we really, really wanted to have 2 control planes on 2 nodes. Seemed that it's possible to do with Mammut. So that was the first thing that worked, and that was kind of like a really initial solution. And PostgreSQL active, just like I said, got released a couple of weeks ago. So this very early technology, we hope we can find a way to get it working with Postgres. So
this is again a very noob question, but is Postgres instead of Marmont or in addition to Marmont?
that would be instead of Mammut, because
Instead
there's
of.
no CDC. It's active replication, which is
Okay.
supposed to be more consistent. Also, this Mammut is not a bad thing, considering that we are on the edge. Mammut is very lightweight, and Postgres is a very heavy process, so it might not be suitable to all edge cases. If we're talking about like really embedded devices at the edge, we might not want to have Postgres. So having choice is good.
And so in figuring out a way to duplicate the data across the 2 nodes in a way where one could go down, you did manage to solve that, but it's just more complex than you would like it to be, and maybe takes a little longer than you would like for it to resolve. The one that actually worked, was that with Marmont or was that with Postgres? Marmont. Okay.
Yeah, so, I mean, sticking with what our design goals are, and trying to keep it simple. Marmot is very simple. Turn it on, as Oz mentioned. You put a couple flags and it's done. The challenge becomes in the logic on how you fail over. You don't want to have 2 active nodes. You need to make sure that everything is in sync before you fail over. What happens when it's just a abrupt, oh, I pulled the power, and what happens when it comes back online? And that orchestration is it turns out, is quite complex. If we could just leverage what Kubernetes does already, and we had a backend that supported that, this becomes a very, very easy problem to solve. But as we saw today, there's a lot of choice, but also not very many of them are very easy to implement.
So now the challenge is to get control plane on both nodes.
Yep.
And that you're hoping to solve with PostgreSQL, but that's what you're currently working on right now.
Yeah, we have a couple of options that we're looking at. Postgres is one. There's a couple of other design choices that we've made and internally are testing, but the one that seems most promising right now is that.
So is there anything you'd like to add to my child's mind to recap of your very wonderful and detailed presentation?
No, I mean, I think ultimately our goal is to try and keep it simple, but we're solving for a problem that at mass scale, which is what we're talking about. We're talking thousands and thousands and thousands of locations. We feel like we've done a very good job with Edge in general. We have a platform that provides consistency, and it provides our customers easy deployment, but this is an ask. I want to chop off a node. $1,000 a node times 1,000 locations is a big number. And especially when organizations are looking at maybe leveraging other technologies. Oh, maybe I want to do something with, AI, but I don't have the budget to be able to do that because I have to spend $1 million more every time we roll out a new thing. So being able to divert those funds for our customers is something they've asked for. And if we can, and I think we will in the next few months, you'll see, we're going to have a very elegant solution to solve that problem.
This has been super cool. I've learned so much. Is there anything you'd like to say in closing before I read the ending script?
No, just look forward to seeing you at KubeCon. Stop by our booth. And oh, there's a question that popped in.
Oh, this is okay. Question not related to this presentation, but have you tried running Kine in RKE2 and using PostgreSQL?
Not RK2, but we have with kubeadm. So we shim Kine with that, and that works. We think it will work with RK2. That is one of our target distributions. And as I mentioned before, the big reason for that is FIPS. But yes, we are looking at that.
Cool. Thank you for your question, Ferdinand. And thank you so much. I'll be at KubeCon too, so I look forward to meeting you both in person. And those watching this, please do say hi if you see any of us around. We'd love to talk. All right, so thanks everyone. Thank you so much for joining today's episode of Cloud Native Live. It was great to have Justin Barksdale and Oz Taram here teaching us about using 2-node HA for Edge Kubernetes. It's a new approach. It's so exciting. As always, I love the interaction and questions from chat. Thanks for being amazing. And thank you so much for those of you who watched the recording. Here at Cloud Native Live, we bring you the latest in Cloud Native code at noon US Eastern. We're going to be taking a break for KubeCon and then Thanksgiving and holidays, but we'll be back in December. Thanks so much for joining today. Thank you so much, Justin and Oz, for sharing your expertise and your journey. It's been so fun. And thanks to those who watched the recording. I'll see you soon. Bye.
Thank you. See you soon.